Hi guys, how are you all doing? So yesterday we started real numbers and we come across the definition of real numbers. Real numbers are basically a collection of rationals and irrational numbers. Today we're gonna learn more about them. We will learn about Euclid's division lemma, then fundamental theorem of arithmetic, then I will tell you the definition of LCM and NCF, and if times allow it, then we will do some NCERT questions. Okay, so let me just jump the app. Okay, so this is last we have done real numbers, connection of rationals and irrational numbers. So today pen is working right. Okay, I have to zoom it. Okay, yeah, I can write. Okay, so real numbers, right? We're gonna do. Oh man, I need to zoom it. Oh, that's too much. I think 110. Yeah, I think that would be good. So let's start with Euclid's division lemma. Okay, there has to be two M's in it. Lemma. So what is Euclid's division lemma? Basically, it means dividend equals divisor multiplied by quotient plus remainder. And there are some properties. One of the properties is that remainder is less than or it will be equal to. It can't be equal to divisor, right? Because if it is equal to divisor, then we can always just get remainder 0. So this is wrong. It can't be equal to divisor, and obviously it will be greater than or equal to 0. So this is basically Euclid's division lemma, that dividend is equal to divisor multiplied by quotient plus remainder. So what does I mean by that? So let me just give you an example. Suppose we divide 11 by 5. So we will get something like this, right? 5 2s are 10, and when we will subtract 10 from 11, we will get 1. So let's just verify that whether dividend is equal to divisor plus quotient multiplied by quotient plus remainder holds or not. So here the number by which we are dividing is called divisor, the number which is being divided is called dividend, and what we get as a multiple is quotient, and then without going to the decimal expression, what we get here after the subtraction, and we can't go further without using decimal, is called remainder. So here dividend is equal to what? 11, because 11 is being divided. Divisor is equal to 5 because 5 is being used to divide 11, right? Quotient is what? Quotient is this multiple 2, and remainder is what? Without resorting to decimal expansion, then the step after which we can't go further, and the product we get here is the remainder, so it is going to be 1. So 5 2s are 10 plus 1, this is equals to 0, and on the left hand side there is also 11. That means that this statement, this lemma holds true. So this is simply what Euclid's divisor lemma is. You just have to remember that what are divisor, divider, and quotient and remainder, and also this property. This property that remainder will either be strictly less than divisor or it will be either greater than or equal to 0. What do I mean by that? See, when I divided 11 by 5, I stopped at the step when I get 1 as a remainder. Why? Because now I have to use decimal expansion to solve it further. It can be solved further, but I don't resort to decimal expansion now. So that simply means that 1 will be a remainder. Now you will notice that 1 was strictly less than 5 and it was greater than or equal to 0. So 1 holds between here. Suppose if I draw, suppose this is 0, this is 1, this is 2, this is 3, this is 4, and this is number line. Obviously the measurement is not accurate, but what I'm trying to do here is to prove that this equation, this inequality holds here. Like 1 lies between 0 and strictly less than 5. Okay, so why do remainder has to be strictly less than divisor? Why can't it be equal to divisor? So suppose let me give you an example. Let us divide 5 and this time we will have y divisor. Y divisor can't be equal. Okay, y remainder can't be equal to divisor. Okay, let me just give you an intuition first. Suppose that the remainder is actually equal to divisor. Suppose I don't know what I was doing, but suppose I was dividing some number and after subtracting I got 5, and suppose my divisor is also 5. Then can 5 be a remainder? No, it can't be, right? Because I can always, whatever the question here is, I can simply write 1 after it, and 5 minus 5 is going to be 0. And because 0 appears, so we don't have to do it further, so the 0 will be the remainder. So this was basically intuition that if remainder is ever equal to divisor, we can simply multiply the divisor by 1 and we will get the divisor itself, and then we will subtract it from the supposed to be remainder, and then we will get 0. And because as soon as we get 0 in the division, we stop. Like that is the ultimate step now, that we don't have to do it any further, it is solved. So that's why remainder can't be equal to divisor. But obviously remainder has to be greater than or equal to 0, because at max what remainder, when we subtract a natural number and two natural numbers from one another, what happens? Assuming, suppose, let me take an example, 121, and let me divide it by 11. So 11 ones are 11, then I will get 1 and 1, then 11 ones are 11, and then we get 0. See, if I get 11, that is remainder here is what? 11, supposed to be remainder, this is not remainder. And divisor, so divisor here is also 11. So when this supposed to be remainder is equal to divisor, what I did, I simply multiplied this divisor with 1 and I get divisor itself. And then when I subtract it from the supposed to be remainder, what I get? 0. That's exactly the reason why remainder can't be equal to 0. So why can't remainder ever be less than equal to 0? Why it can't be less than equal to 0? Suppose y remainder can't be less than equals to 0 to hold करता है, it do hold, right? So why it can't be less than 0? So let me take anything, any number. Let's say I have to make sure I get remainder. So I could simply write 17 and then I will divide it by 3. So what would I get? 3 5s are 15 and then 2, right? So you see that if this is the dividend, whenever I'm using the like this quotient, I make sure that I get some multiple of this divisor, that is 3. I get some multiple of 3 such that this number is either equal to 17. And if 17 doesn't occur in the table of 3, then I make sure that I get something that is strictly less than 70. That means when I would have to subtract the two numbers, in this case 17 and 15, this number will be a natural number, this is again a natural number, and this is strictly less than this, right? So if this number is bigger or greater, and this is uh, smaller, then when I subtract both of them, what I'm gonna get? Obviously a positive natural number, right? But that is only the case when we can't get the dividend itself. So suppose if I write 18 divided by 3, I can simply write, because I know that 3 multiplied by 6 equals to 18, I can simply write 6 here and then 18 and then subtract both of them and then comes 0. So this number can either be equals to 0 or either it can be some positive natural number or simply a natural number, right? So it is either a natural number, that means 1, 2, 3, 4, something, one of it, or either it is 0. And we have learned this yesterday, that this collection is basically called whole numbers. And if R is one of the whole numbers, it has to be greater than or equal to 0. So, okay, my page ended. I will simply jump to the next page. Let's change the color to. Okay, so that would simply what Euclid's division lemma is, that dividend is equal to divisor multiplied by quotient plus remainder, and you will always have to remember this, the remainder is less than divisor but strictly less than divisor, and it is greater or equal to 0. This, if you are getting confused, when I write this this sign, this sign, this sign, or this sign, they are called inequalities. So whenever a mathematical expression contains any of this, right, instead of simply writing equals to, if it contains one of this symbol, then we see that expression as inequality. So when I say this, that a, now to learn which one of this is gonna be less and which one of this is gonna be large, is simply look at the points. So here this symbol has one dot here, that means this is gonna be smaller, and it has two dots on B side, so B is gonna be large. And when I write it like this, it means that either this or this, that is, both of these cases can be true. A can be strictly less than B, or A can be equals to B. Both of these condition holds, and to write both of these in one expression we use this symbol less than or equals to. Okay, so let's just move to fundamental fundamental theorem of arithmetic. So what is fundamental theorem of arithmetic? I told you composite numbers yesterday, right? I have told you that numbers which has more than two distinct factors are said to be composite numbers. And what are prime numbers? Prime numbers are basically natural numbers which has exactly two distinct factors. And when I say factors, I simply means that the number should come in the table of the factor, supposed to be factor, right? So when I say fundamental theorem of arithmetic, what it in simple language it means that every composite number can be written as product of prime numbers in a unique way if order, don't get confused by order, I will simply write arrangement of prime numbers doesn't matter. So let us just understand this definition. Every composite number. So first of all, when we are applying the fundamental theorem of arithmetic, we will make sure that the number we are checking it on is a composite number. So let's say, let me give you one composite number, say 10. So 10 is a composite number. Why? Because it has factor, because 1 multiplied by 10 equals to 10. So 1 is a factor. 10 multiplied by 1 equals to 10. So 10 is a factor. And 2 multiplied by 5 equals to 10. So 2 is a factor. And 5 multiplied by 2 equals to 10. So 5 is a factor. So it has 1, 10. So it has 1 as a factor. And it has itself as a factor. But then it has more than two distinct factors, which are 2 and 5. So this is going to be what? Composite number. So we can apply fundamental theorem of arithmetic on 10. So the theorem says that every composite number can be written as product of prime numbers in a unique way. So first of all, we're going to simply write 10 as a product of prime numbers. So if I write 10, like there are only 4 ways to write 10, right? 1 multiplied by 10, but then 1 is not a prime number, right? So if I have to write 10 as a product of prime, then this is not a correct method. If I write 10 multiplied by 1, then again 10 is not a prime number, neither 1 is. So this is also not a correct way to write it as a product of prime numbers. If I write 2 multiplied by 5, 2 and 5 both are prime numbers, right? So I can write 10 as 2 multiplied by 5, and this composite number has been written as product of prime numbers. But 10 can also be written as 5 multiplied by 2. So now to write 10, that is our composite number, as a product of prime, there are two ways, right? We can simply write 2 multiplied by 5, or we can write 5 multiplied by 2. So when I say that can be written as product of prime numbers in a unique way will hold only if order or arrangement of prime number doesn't matter. That means that writing 2 multiplied by 5 or 5 multiplied by 2 is equal, yeah, same way, is same. So 2 and 5 are primes, and if their order, their arrangement basically means that which number we gonna write first doesn't matter. So if I write 2 multiplied by 5 or write 5 multiplied by 2, both of these ways are considered the same, then because these both are same, so this won't be two ways, but this will be only one way to write 10 as a product of prime, which is either 2 multiplied by 4, 5 multiplied by 2. So this is what I meant when I say that every composite number can be written as product of primes in a unique way if the order of a prime number doesn't matter. So let me take another example. Let's move on with let's say 625. So first of all, I have to write 625 uh, as a product of prime. Maybe okay, let me just start. First of all, because it has last digit, advanced digit, it has 5 in it, so we are sure that it will be divisible by 5. So if I divide 625 by 5, I'm gonna get, I divide 625 by 5, I'm gonna get 5 ones of 5, then 1, 2, 5 2s are 10, then 2, 5, and then 5 5s are 20, sorry, 5 5s are 25, and the remainder will be 0. So let me write this. So here 125, 625 can be written as 5 multiplied by 125. Again 125, because it has 5 in one digit, it will be divisible by 5, so it will occur as 2 5, and then again 5 multiplied by 5, and 25 can be written as 5 multiplied by 5. So this was a composite number. Why? Because it has factor 165 are definitely its factor, but it also has 5 as a factor. There are also more factors, like there is 25, there is 125, 5 to the power 4. So number of divisor will be 5 to the power 5, right? So 1, 2, 3, 4, 5. These are all of its factors. So this has more than two distinct factors, so it is going to be a composite number. So this is a composite number, and this is me writing it as a product of prime numbers. So this is what I meant when I say that every composite number can be written as product of primes, and if the order arrangement in which the prime numbers are being product with one another doesn't matter, then the writing of composite number as a product of prime is unique. And factorization is another term. Let's see, factorization. I think STIOM is used for it. Factorization is simply means writing a natural number as product of primes. Factorization is nothing but whenever you write a natural number, it can be a prime, it can be composite. If it is a prime, suppose 2, then I can simply write 1 multiplied by 2. But obviously 1 is not going to be prime, so we can simply write 2. Because there is no other way, right? 2 is not going to have any other factor. So we have to write 2 as equals to 2. But suppose if 6, we have to write 6 we have to factorize 6. So what will we do? We will simply write it as a product of prime numbers. So because we can write 6 as 2 multiplied by 3, and because 2 and 3 both are prime numbers, so we have written 6 as a product of two prime numbers. When I say prime numbers, they doesn't needs to be distinct. They can be equal, right? For example, in this one, when we write 625, we have only taken 5 as a prime number, but because it is written as 5 multiplied by 5 multiplied by 5 multiplied by 5, that is 5 is being multiplied 4 times. So this also falls in the definition of writing a composite number as product of primes. So factorization, writing natural numbers as a product of primes. So this is what simply factorization means. There is nothing new to it. We simply have to write them as a product of primes. But this method has very important application. I think later in the lecture we will be able to find out that why we are actually studying factorization, like what is the significance of the fundamental theorem of arithmetic. So before that, let me add a page. Uh, After, yeah, I think I will need another page after it. Okay, let me just go to it. Let me zoom to 1110. Let me switch up the pen. I think I will go back to yellow one. Let me just go back to the green one. Okay, so before we do that, I think I'm gonna just jump to fundamental theorem of arithmetic. We have learned that, and okay, so there is this question, this one. Example 1. Consider the number 4n where n is a natural number. Check whether there is any value of n for which 4n ends with the digit 0. Okay. So the question here is simply that we have to check that 4n ever ends with digit 0. Only. When I say ends with digit 0, it simply means that when I express 4n in much less simpler terms, then once a digit has to be 0. For example, uh, let's say 4 multiplied by 5. 4 multiplied by 5 is going to be what? 20. So this ends with digit 0, right? If I write 10 multiplied by 2, it is going to be 100. So this 10 multiplied by 2 ends with the digit 0, right? So this is what I mean when I say that the question is asking us that is there any value of n where n has to be a natural number such that 4n ever ends with the digit 0. So what we will simply do, we will find out that suppose n has to be a natural number, so the possible values of n are 1, 2, 3, and then we can go on. Suppose we take 1, it will be 4. Suppose we take 2, it will be 4 4s are 16. Then suppose f to the power 3, it will be 16, 4 square multiplied by 4. So it will be 16 multiplied by 4. That will give us 64, right? In the same manner, we can move forward with it. But I'm gonna tell you exactly why. The answer of this is it will not end with the digit 0. And I will tell you the reason behind it. You see, in both of these examples, this 20 and this 100, you will see a common property that if a number has to end with 0, it must be written as whatever, I don't know what the number will be multiplied with, but it must be multiplied by 10. In this case, it has to be 2. The number has to be 2. Here, I don't know what the number has to be multiplied with, but if it ever has to end with the digit 0, it must be multiplied by 10. And in this case, to make 100 from the multiple of 10, we have to write 10. And this is the 10, And the only way 10 can be formed is if we write 2 multiplied by 5. Suppose I have to write 10 is a composite number, right? So suppose if I have to write this composite number as a product of prime, what will I write 10 as? 2 multiplied by 5. In a similar manner, this 10 has to be written as 2 multiplied by 5. Now we can also like further simplify 10 into 2 multiplied by 5, but we won't be needing it. What I'm trying to tell you, what I'm trying to explain you here is that if a number has to end with 0, it must be multiplied by 10. The number, not the number itself, but there has to be number, a natural number, but has to be multiplied by 10. Until unless this happens, we are not gonna get 0 as the ones digit. And when we write 10, 10 is obviously a composite number. When we write 10 as a product of prime, we get 2 multiplied by 5. So this 20 equals 2 multiplied by 2 multiplied by 5. That means that this 20 is composite number because it has more than two distinct factors. So when I write composite numbers as a product of prime, and if in its factorization, this method writing as a product of prime is simply factorization. So when writing a composite number as factorization, if 2 and 5 both doesn't occurs at least once, they have to come once now. So suppose if only 2 comes and 5 doesn't come, then what are the number will be? 2 multiplied by 2, which is equal to 4, but it doesn't end with 10, right? If only 5 would have occurred, it would have become 10. But this is the case, we get 10 as a multiple only if 2 and 5 occurs at least once. They have to appear as a pair at least once, right? So that means that for a number to end with 0, when I write prime factorization, when I write it as a factorization, it must have 2 and 5 at least once. And if a number, when written as prime factorization, 2 and 5 occurs, because 2 divides this side, I can divide 2 multiplied by 2 multiplied by 5 by 2. It will simply give me 2 multiplied by 5. Because 2 divides this side, right hand side, and right hand side is equal to left hand side. So the left hand side must divide 2 must divide the left hand side 2, right? In the similar manner, because 100 is written as 10 multiplied by 2 multiplied by 5, because this side can be divided by 2, and because this side is equals to left hand side, so right hand side must be divided by 2, right? And because this side can now be divided by 5 also, so this side must be divided by 5 also. That means that if a number has to end with 0, when I write it, if it is a composite number, if I write it as a prime factorization, 2 and 5 should appear at least once. And if that is happening, because right hand side and left hand side both are being equal, so if 2 is dividing right hand side, then 2 must divide left hand side too, and if 5 is dividing right hand side, then 5 must divide left hand side too. So in the similar manner, coming back to the original question, if 4 and ever ends has to end with digit 0, suppose I assume that this is true. 4n somehow ends with 0. I don't know what I have to multiply it with. Suppose k. I don't know what it is, but because if it ends with 0, it must be multiple of 10, right? And if it is a multiple of 10, I can simply write it as 2 multiplied by 5, because 2 is dividing right hand side. So 2 must divide left hand side, right? So because 4n can be written as 2 to the power 2, then n, which is basically equals to 2 to the power 2n. And because n is a positive number, so this will either be 2 to the power 2 or 2 to the power 4 or 2 to the power 6 अगर if n equals to 1, if n equals to 2, if n equals to 3. Okay, the page ends here. Let me add another page. I should go back to the yellow option, right? So before I move on, let me just simply clarify here. Where is my page? Yo, where is my page? Wait a minute, oh man. I just wasted this amount of page. Why? Okay, so when I write 4n has to the power 2, and if n equals to 1, we're gonna get to the power 2. If n equals to 2, we're gonna get to the power 4, and if n is equal to 3, we're gonna get to the power 6. And because all of this is divisible by 2, this also is divisible by 2, and this also is divisible by 2. Basically, even if I move further with n, whatever number I'm gonna get, it will be divisible by 2. So one condition is being held, that the number itself has to be divisible by 2. But because this right hand side is also being divisible by 5, so and because this right hand side equals to left hand side, so left hand side must be divisible by 5 too. So 4 to the power n must be divisible by 5. For that to happen, because 5 is a prime number, the only way 5n will ever divide 4n, if 4n can be written as, I don't know, let's say m multiplied by 5. Just think about it. 5 is a prime number. So if I say that 5 divides 4n, then 4n must be written when in prime factorization form, it must be written as like this, m multiplied by 5. I don't know what m is. M can be another, like it can be expanded into m1 multiplied by m2 multiplied by m3 and so on. But whatever it is, because if I'm assuming 4n can be divided by 5, it must have a factor 5. And if it has a factor 5, then that has to be a number multiplying 5 by with, I'm gonna get 4n. And basically, if 4n is being divisible by 5, then 4n must comes in the table of 5. That means 5 multiplied by something m, where m is a natural number, must be equals to 4n. The problem here is 4n, we have seen that 4n can be written as to the power 2 and n, and no matter how much I increase n, it will always be power of 2. So it will be 2 multiplied by 2, 2 multiplied by 4, 2 multiplied by 6. But never ever will it ever happens that there comes a stage where I can write for some, suppose for n equals to p, I can write 2 to the power ps 2q multiplied by 5. I can't write this, because if I can write it like this, because 5 is dividing this side, 5 must divide this side too, but 5 can't divide 2 now, right? 5 can't divide 2, so this means that this is an absurdity, and we can't do this. So as I was saying that because 5 can't divide, where I was, okay, 5, because 5 can't divide 2 and 2 to the power anything, like you can write 2 multiplied by 17, 5, 3, anything, because 5 doesn't divide 2, 5 will not be able to divide 2 to the power some p, some natural number 2. And if that doesn't happen, that simply means that 4n, because 4n is simply written as to the power 2n, right? So 4n can also be not be divided by 5, and because it is not being divided by 5, I'm never gonna get at least 1, 2 and 1, 5 in its factors, or as when I write it as a prime factorization, but I'm not gonna get 2 and 5 at least once. And if that doesn't happen, the number, whatever it will be formed, it will never be a multiple of 10. And if it is not a multiple of 10, the number itself will never end with uh, 0 at its ones place. So this was the question, that for an ever ends with digit 0 or not, the answer is not, because for that to happen, it must be a multiple of 10. And for it to be multiple of 10, it must have 2 and 5 appear at least one in its prime factorization, but we have clearly observed that it doesn't occurs. Okay, so let me just scroll up to the page, and we will move to the next question. Find the LCM and LCF. Okay, I have to teach you LCM and LCF first. Why you do it? Okay, so LCM and LCF. See, LCM and LCF are just new terms, but there will be nothing new we will actually be doing. We will simply be writing numbers as um, prime factorization. We will simply writing them as a product of prime numbers. So let me just say, I will give you the basic definition of LCM and LCF first, and then we will move on with some examples. So let me just see HCF. What is HCF? Full form is highest common factor. And what it simply means that first of all, HCF and LCM are being discussed between two natural numbers. So whenever we are discussing HCF and LCM, we have to make sure that we have two numbers. So suppose A and B. We have to find the HCF of A and B. We will simply write prime factorization of A of A, and similarly we will write prime factorization of B, and then we will simply collect common primes. Yeah, okay, let me not write it like this. Let's simply say collect prime numbers with their lowest power from both. So what it simply means that I have to write A and write it as a prime factorization. Then I have to express B in its prime factorization, and then I will simply collect all the primes that occurs in both of the prime factorization with the lowest power. What I mean by that, suppose I have to write let's say 11, not 11, let's go with, let's say 49 and 35. So I have to find the HCF of 49 and 35. So what would I do? I will write 49 as prime factorization. So 49 is 7 multiplied by 7, because 7 and 7 both are primes, so this is the prime factorization of 49. 35 can be written as 7 multiplied by 5, right? And because 7 and 5 both are prime numbers, so we have written it as a prime factorization. Now I can write this as 7 to the power 2, right? And this can be written as 5 multiplied by 7. You see, there is no need to write it like this, 5 multiplied by 7. I have written it like this simply because uh, we have um, we have learned now in the fundamental theorem of arithmetic that writing a composite number with prime, like a product of prime numbers, is unique if order and arrangement doesn't matter. So when we arrange those numbers, we follow this common rule that we're gonna write or we're gonna arrange the prime numbers in increasing order. So because 5 is less than 7, so 5 is gonna be first and then product of 7. There is no need to do it. It's just a simple rule. Rules make it easy for us to um, follow something, right? Like we don't have to think much about it. And this is why I just follow this rule. You don't have to, but okay. So here, 5, the maximum power of 5 is what? 1. The maximum power of 7 is equal to what? 1. Now here, look at this. I can write this 7 square as 5 multiplied by 7 to the power 2, but because no multiple of 5 take place here, I have to make sure that I give it power 0. So now when I have to find the power HCF of 49 and 35, what I will do is that I will write all the prime that occurs. The prime that has occurred in it are 5 and 7. So 5 multiplied by 7, but with the lowest power. So here 5 has the power 0 and here 5 has the power 1. What is the lowest power? So this is going to be 0. Here 7 has 2 powers, 2 and here 1. What is the lowest? 1. So I have to write 7 to the power 1. This will become what? 5, any natural number to the power 0 is always equals to 1. This is one of the identities. Um, right now, you just try to learn this. There is a reason for it, why any natural number to the power 0 is always equals to 1. But right now, you have to just learn it. Maybe we will discuss it further. So 5 to the power 0 is going to be 1. And then 7 to the power 1 is going to be 7. So 1 sevens are 7. That is, 7 is the highest common factor or HCF of 49 and 35. This is what simply it means. So let us just take another example. Let's just go with 121 and 33. So I will write 121 as 11 multiplied by 11. Again 11 and 11 are prime numbers, so we have written it as a prime factorization. 33 can be written as 3 multiplied by 11. Okay, just 3 multiplied by 11. So here 3 and 11 both are prime numbers, so we have written it as prime factorization. Now I can write this as 11 to the power 2. This can be written as 3 multiplied by 11 already, right? So I should not write this, so okay, let me not write it, because it is already in the increasing order form, right? Now 11 square, I have to compare the two prime numbers, so I can write this as 3 to the power 0 multiplied by 11 to the power 2. Why? Because any natural number to the power 0 is going to be what? 1, and 1 multiplied by 11 square is going to be 11 square. Now if I have to find the HCF of 121 and 33, what I simply will do is I will write all the prime numbers. So here 3 and 11 are the prime numbers. 3 multiplied by 11, and I will take the lowest value. So 3 has the power 0, and here 3 has power 1, 11 has power 1. So which is lowest between 0 and 1? 0. So 3 to the power 0. Again 11 has the power 2 and 1 here. What is the lowest between 2 and 1? 1. So 11 to the power 9. This will become 1 multiplied by 11, which is equals to 11. So 11 is the HCF of 121 and 33. Now, let me just talk about the LCM. So what is LCM? LCM basically means lowest common multiple. What it simply means that if I have to find the LCM of A and V, I will write prime factorization of E. Similarly, write prime factorization of B. Then write primes with any guesses what it will be. Like in the previous definition we use the lowest power. In this definition we use the greatest power. To write primes with their greatest power. So let me just take the previous examples. 49 and 30. 49 can be written as 7 multiplied by 7. Thus it can be written as 7 to the power 2. 35 can be written as 5 multiplied by 7. And because the prime numbers that are occurring in the prime factorization 5 and 7, I will simply write it as 5 to the power 0 and 7 to the power 2. Now, LCM of 49 and 35 will simply be prime numbers. So prime numbers are 5 and 7 with their greatest power. So here 5 is power 0 or 5 is power 1. Right? So what is the greatest between 0 and 1? So 1. Similarly, 7. 7 has the power 2 and here 7 has the power 1. What is the greatest between 2 and 1? 2. So here 7 to the power 2. So what I will get? 5 multiplied by 49, which comes out to be 5 times of 45. 5 4s are 20 plus 4, 24. This is the LCM of 49 and 35. Suppose I take another previous example, or maybe I should not. Maybe let me take another example. Let me do. Okay, let's do 16, and let's do let's do 9. So prime factorization 16 would be 2 multiplied by 8 by 2 multiplied by 2. Okay, sorry, it has to be 4. It can be written as 2 multiplied by 2 multiplied by 2 multiplied by 2. 4 can be written as this. Here 8 can be written as this. So this is simply to the power 4. 9 can be written as 3 multiplied by 3, because both of these are prime numbers, so we don't have to simplify it further as in the case with 4, because 4 was not a prime number, it was a composite number, and we are using prime factorization, so we have to make sure that we are writing it as a product of prime numbers. So here it is 3 to the power square. Now two prime numbers 2 and 3 are occurring, so I will simply write it as 2 to the power 4 multiplied by 3 to the power 0, because 3 to the power 0 is gonna be 1. And this can be written as 2 to the power 0 multiplied by 3 to the power 2. I'm again arranging them. I'm arranging 2 and 3 because 2 is less than 3, I'm writing first 2 with its power, and then I'm writing 3 with its power, because it will make it easier for me to compare. If you can skip this part and directly do it, you can do it. There is nothing wrong about it. It's just that it gives me a better visualization and less chances of me doing calculation mistake. So now I have to find the LCM of 16 and 9. So I have to write the prime numbers. The prime numbers are 2 and 3. Now, in case of 2, we have two powers, 4 and 0. We have to choose the greatest for LCM. So among 4 and 0, 4 is the greatest. So 2 to the power 4. Then 3. 3 has power 0 and 2. Among 0 and 2, 2 is the greatest. So 3 to the power 2. So 2 4s are 16. 3 2s are 9. Okay. 2 to the power 4 is 16 and 3 to the power 2 is 9. Then 16 multiplied 9, 6 are 54, 9 ones are 9, 9 plus 5, 1, 4, 4. So this is the LCM. Now, there is one more property that I would like to tell you. Let me just introduce you to that property, and we will discuss it on later, maybe tomorrow. So verify whether this statement that I'm about to write is right or wrong. LCM of AB, whatever this is, if we multiply this with HCF of A and B, we will get A multiplied by B. Now, I'm not writing that, I'm not saying that this statement is correct. I want you guys to check whether this statement is correct or not. What I've written is that no matter what two natural numbers, obviously LCM and LCM only take place between two natural numbers. So A and B are natural numbers. So what I have to prove is that LCM of two numbers A and B and LCM of two numbers A and B, when I product them, they are equals to the actual product of the both of those numbers. So if you can't think of it as a general case, try to take examples, like just simply take examples, maybe 16 and 9. Write down the LCM of 16 and 9, write down the LCM of 16 and 9, and then try to find out that is the product of both LCM and LCM is actually equals to the product of both of these numbers. Try to take 2 or 3 numbers, pair of numbers, and try to verify whether this equation holds or not. And if it holds, then can you find out what exactly is the reason it is holding true? Let me give a hint. The answer lies between the fact that in HCF we take the prime numbers with the lowest power, and in LCM we take prime numbers with the greatest power. That means at the end of the calculation, when we multiply both LCM and LCF, we have taken all the powers of primes. Like we only have two choices, right? So either one of them is going to be lowest, and either one of them is going to be greatest. If we have taken both of these, when I do product them, I'm definitely going to get the product of both of these numbers, right? But is it really true? Just think about it, and we will discuss it later tomorrow. Thank you for staying up to this mark, and please subscribe.